Okay, I'm going to do another example of finding a Thevenin equivalent circuit. So we're supposed to find Thevenin equivalent. So in this case, we're given a 400 nanofarad capacitor. We're given a dependent power supply, which is 5 I delta. And then we're given 600 microhenries. And then a 30 ohm resistor. And then the problem also says that the circuit is operating at a frequency of 100 kilorads per second. So first thing we should do, of course, is change everything to impedances. So if we do these, we have a capacitor and inductor. So remember, impedance for a capacitor would be negative J over omega C. And now, because this is in radians per second, whoa, what did I just do there? Let's undo that. Because this is in radians per second, this is omega. So then this would be minus J over 100K times 400 nano. Now you need to keep your engineering notation straight. Some of you forget nano and kilo and what they stand for. Nano is to the -9 power. And then if I do this, we wind up with J25, that would be negative J25 ohms. And I'm going to go ahead and redraw the circuit, so I'm not going to worry about labeling it on the original. And we have ZL, which would be J omega L. So this would be J times 100K times 600 microhenry. So which gives me J60 ohm. So I'm going to redraw this circuit, and then we'll talk about finding the Thevenin equivalent here. What am I doing here? Redrawing the circuit. Sorry, I got myself slightly distracted there. And I think I forgot to label in this very first circuit here. I delta is the current through the 30 ohm resistor, except it's actually going the other direction. It's going that direction. Okay. So we have I delta. And then these are now going to be negative J25. And this is still 5I delta. And this is now J60. And of course this is still 30 ohms. So what do we have to do here? Well, we have to find V Thevenin and Z Thevenin. Now I claim that V Thevenin is easy to find. We don't have any independent power supplies, so with no independent power supplies, this just means that this is 0 volts. So V Thevenin is just equal to 0 volts. And that's because we have here, let me put it in parentheses again. I've said it many times. No independent power supplies. Because remember, this is a dependent power supply, so it depends on the fact that there's got to be a current here. Well, there's nothing that's creating any kind of current or voltage in this circuit, so the dependent power would be 0, so voltage is going to be 0. Now, remember though, to find Z Thevenin for dependent sources, or when we had dependent sources here, one thing you had to do, there was, well, you could find I short circuit and V open circuit. That's not going to work here because we don't have any independent power supplies. But if you remember, you could apply a test voltage. So I'm just going to apply the easiest test voltage I know. You can pick any test voltage, but I'm just going to do one at an angle of 0 degrees. Because this is in polar here. And so this is my test voltage, V test. And then what I need to figure out is if I draw a loop like that, this would be my I test. And so Z Thevenin would equal V test over I test. Alright, well, we're just going to, since I need to figure out what I test is, it makes sense to do a loop analysis. And so I'm going to draw one other loop here. But I'm not going to draw it in the same clockwise direction because I delta is counterclockwise. So this would just be my I delta here. Because then we have a very simple set of loops we can write. So if we go for loop I test, well, you'd have 1 is equal to negative J25 times I test, because it's V is equal to Z times I, plus 5 I delta plus J60, and then this would be, well, I test and I delta are going in the same direction, so this would be I test plus I delta. So let's simplify this out, being a little bit careful. So I'm going to do it in 2 steps just so I don't make a silly mistake myself. Okay, so then if I look at this, I'd have 1 is equal to, well, I've got negative 25J plus 60J. So I believe that should get me 35. Let's just double check here. J35 I test. And then I have 5 plus J60 I delta. And that's my first loop here. Now the second loop here, I'm going to have this off the screen here, is pretty simple. We can see it's 30 times I delta plus J60 times those 2 currents. So my loop I delta is going to be 0 is equal to 30 I delta plus J60 I delta plus I test. So we get 0 is equal to, well, this would be J60 I test plus 30 plus J60 I delta. So what I have here is a system of equations that I need to solve. Now, we need to remember how to do this. Now, depending on the model of your calculator might be able to do this directly in a matrix by putting complex numbers in, but I use the TI-84, which you can't put complex numbers directly into the matrix, but we can write the matrix in the following here, where if I do this for my matrix and I put in, so it's going to be 0, 35, negative 35, 0. That's for this I test term. And then I would put in 5, 60, negative 60, 5. And that again would be for this I delta. And then I'd have 1, 0, 0, 1. And then I'm going to do the same thing for the next equation. So I'd have 0, 60, minus 60, 0. And then we'd have 30, 60, minus 60, 30. And then just a bunch of zeros here, because that's what it's equal to. And then remember, we put this then in reduced row echelon form, which I'm going to pause the recording here so I can type this into my calculator and do that. And so I've plugged it into my calculator now, and the answer you wind up with, or at least I did, and I double check my entries. You have your identity matrix here off on the left hand side, and then we have 0.032, 0.024, negative 0.24, 0.32, negative 0.16, negative, actually I'm making mistakes here. This is 0.024, 0.032, I'm forgetting to put in the extra 0 there. This would be negative 0.016, negative 0.032, 0.032, negative 0.016. And so that's what it gets. Now if you had an engineering notation, it would actually put it in the engineering notation nicely. And so what this means here is that I test is equal to 32 plus J24 milliamps. And that's coming from here. Then we also have, we don't need it for the problem here, but we also have that I delta is equal to 32, negative 16 minus J32 milliamps. And that's coming right from here. And so doing those here, what else do we have? Well, we can finally get that Z Thevenin is V test over I test. So that's 1 divided by 32 plus J24 milliamps. Which if I do that on my calculator, I wind up with 20 minus J15 ohms. So remember, what are we finding here? The equivalent, Thevenin equivalent, and we had that V Thevenin was 0 volts because there was no independent power supplies. And so what do we wind up with here? Then my Thevenin equivalent is just an impedance component, and it would be a resistor, 20 ohms, and it's negative, so it's a capacitor, negative J15 ohms. So this would be my Thevenin equivalent. Alright, so that's enough of the Thevenin stuff. The next set of examples we're going to look at are actually just ones where we're going to be looking for voltages, like just doing a nodal analysis, finding a current or a voltage.